Analytical Chemistry 1, Lesson 9. Uncertainty in a measurement is the result of random errors. We will assume from here on that you have appropriately analyzed your experiment, confirmed the results, and removed any systematic errors. What we need to do now is to decide how to measure and report the uncertainty in our results. If I mix up the words error and uncertainty from here on, consider them the same thing. We use statistics to describe and analyze our data and to draw conclusions from our work. Descriptive statistics are used to describe and characterize a set of data. The central tendency of a set of data is described by the average, or the mean, the median, or the mode. The dispersion of a data set is described by the variance, or the standard deviation, as well as things such as skewness or kurtosis. And the number of samples we obtain also make a difference on the uncertainty of our conclusions. These three parameters are perhaps the most fundamental measures that can describe a set of data, and drawn from these data are two more commonly encountered parameters. Well, first, the standard error of the mean is both conceptually and significantly different from the standard deviation. And from that, we will develop what are called confidence intervals. Look here at the distribution of a set of data. Here is a line graph on which we will place the results of some measurements. Let's say that it is measuring ppm concentration. I will again place a dot on this line to represent the result of each measurement. Here are 5 measurements. Again, they have been chosen randomly from a normally distributed population with a certain mean and variance. The problem, as is generally the case, is that we do not know what those values are. This is a certain distribution of data, and we can describe this distribution by calculating the two parameters, the average and the sample variance. Here again are the equations we use to find those two parameters. Recall that these are also known as the first and second moments of the distribution. You see how the variance involves the square of the values. To get a measure that works well with the average, we take its square root and call that the standard deviation. Here are the 3 essential parameters that characterize this particular data distribution. Number of samples, which is 5, their average, which is 5.10 ppm, the variance, which is 0.371 ppm squared, and the standard deviation, which is just the square root of the variance, 0.609 ppm. Now, I said that there were 3 parameters because the variance and the standard deviation are both measuring the same thing. The variation are spread in the data. The question, of course, is how confident should we be that the average of 5.10 ppm is representative of the true but unknown population mean? If we take some more measurements, perhaps that will be revealing. Here are another 5 samples, also chosen at random from the same population. Now we have 10 samples. This is now a new data distribution, and its parameters are n is equal to 10, average is 5.25 ppm, and standard deviation is 0.708 ppm. So is this 5.25 a better value than the previous one? How do you decide? 10 samples seems like they should be better than 5 samples. So let's continue and take another 10 samples. Now we have a total of 20 samples, selected randomly from the same normal distribution. Now the distribution of these 20 samples is represented by n is equal to 20, average 5.27 ppm, standard deviation 0.592 ppm. Let's continue to explore the trend with another 10 samples. This is now a new data distribution. Here are the parameters from this one. Note that the average of these 30 data points is now 5.22 ppm. Let's do another 10 samples. Now we have a total of 40 data points, all representing experimental attempts to measure the same concentration. The parameters are here with an average value of 5.12 ppm. Seemed like we were homing in on something around 5.2, but now with additional data, we're back to where we started, around 5.1. Our last step is to take 10 more samples. We now have 50 total measurements. Each one is different only due to random errors arising quite naturally in the experimental process. The average is now 5.11 ppm. So think about this for a minute. Look at the standard deviation. It is not getting substantially smaller in any obvious way. The square root of the variance, the standard deviation, is always trying to describe how that particular data set is distributed, and it is always distributed. There is a population variance to which the experiments will converge if we do hundreds or more experiments. But don't you have the feeling that taking more data points should narrow down the answer for you? Well, it should, and that is what the standard error of the mean tells us. Remember, the standard deviation is telling us about the distribution of data points for a particular data set. The standard error of the mean, however, is telling us how much variability we anticipate in the value of the average of that distribution. The calculation for this standard error is straightforward. Divide the standard deviation by the square root of the number of samples. As n increases, the standard error will get smaller, and as n approaches infinity, the standard error approaches zero. The standard deviation of the distribution will be a non-zero value, but with more samples, you have increasing confidence in the value of the average you calculate. Being ever closer to the population mean, the error gets smaller. Here are the standard errors of the mean associated with each of these samples. Note how the standard error does get progressively smaller as the number of samples increases. Now, a word of warning, it is common for students and scientists for that matter to confuse the standard deviation and the standard error. Be alert. The final piece to discuss is that of confidence intervals. Now, I'm only going to tell you half the story right now. We need a few more ideas before we finish it, but this gets the essence. A confidence interval is defined as centered on the sample average, with endpoints a fixed distance above and below that average. The endpoints are determined as being some factor of the standard error of the mean. The constant k in the equation as written here is that scaling factor, and I won't say now how to choose its value. We will get to that in a subsequent lesson. But its value is commonly taken to be 2. It can range from something less than 1, though that's seldom useful, at least in the physical sciences, up to larger numbers like 5 or even 10. It could go higher, but then it's also seldom useful if it does. The constant k is chosen based on the number of samples used to find the mean and on a desired level of confidence, 90% confident, 95% confident, and so on. A few things to note. A confidence limit is not a multiple of the standard deviation. Rather, it is a multiple of the standard error of the mean. Now, yes, I know that the standard error is scaled from the standard deviation, but I want you to be sure that you use the standard error of the mean and not the standard deviation directly in the equation given here. Well, they are so closely related by the square root of the number of samples. It is also important to be sure you understand what is meant by the confidence interval. If we have constructed a 95% confidence interval, it does not mean that we are 95% confident that the interval contains the true population mean. In fact, as I think about it, I'm not even sure what that would mean. And yet it is a common description one hears about confidence intervals. Instead, what it means is that if you were to duplicate the experiment, produce a new confidence interval each time. For instance, let's say we took 10 samples, found the mean and the standard error of the mean, formed the 95% confidence limit. What that means is that if we did that 20 times, that is, took 10 samples, found the mean, standard error, confidence interval, that if we did it 20 times, then we could be confident that at least 19 of those confidence intervals would include the population mean. 19 out of 20 is 95%. Now we will encounter this again. Once we know how to describe our results, we can go further and carry out statistical tests. This is called inferential statistics, to answer questions and reach conclusions from our data. When we studied the nitrite concentration in the aquarium, we described our results with the average, the variance, and the number of trials. But then we wanted to know, did our results suggest that our fish were at risk because of the nitrite? That requires a test. Statistics tests are based on what is called the null hypothesis. The null condition is generally best described as the status quo, the normal operating conditions. If everything is working fine, then that is described by the null hypothesis. The first step is to articulate the null hypothesis. In the case of our aquarium's nitrite concentration, we hypothesize that the nitrite concentration is less than 5 ppm because then everything is fine and no problems have arisen. We must also articulate an alternate hypothesis, which in this case is that the nitrite concentration is greater than or equal to 5 ppm. The alternate hypothesis is always mathematically the opposite of the null hypothesis. Here we have the mathematical region less than 5 and the region greater than or equal to 5. We label these two hypotheses H0 and HA. There will be two kinds of statistical tests, referred to as either one-tailed or two-tailed tests. And the one-tailed test can be either right-tailed or left-tailed. Our statistical tests are designed to reach a binary conclusion that is worded in a very particular manner. Our tests will either allow us to reject the null hypothesis, or they will fail to reject the null hypothesis. Now note that wording. We do not end up proving either hypothesis. We can only reject or not reject the null hypothesis with a certain level of confidence. This is not generally what the public wants their scientists to tell them. They want, is it A or B? And they're frustrated when scientists have to be more modest with their claims, but that is the nature of our experimental science. Now we'll see more about this shortly. This aquarium case is a one-tailed test because we are only interested in knowing if our concentration exceeds a threshold, 5 ppm in this case. In fact, it is a right-tailed test. If our statistics go far enough to the right, on a number line for instance, we will reject the null hypothesis. We will see graphically what that means. We will commonly encounter two-tailed tests also. Does the true concentration lie between 4.5 and 5 ppm? In such a case, we consider it being either greater than some limit or less than some other limit. We need to decide what test we will be doing. And we next need to choose a statistic that we can use to evaluate the hypothesis. Such statistics typically consist of a ratio of A over B. The numerator A is a function that involves the average or mean of the data. The denominator tells about the distribution of the data and involves the standard deviation of the results. Different tests use different A's and B's. There are many tests and their associated statistics. The ones more commonly encountered in analytical chemistry are Z-tests, T-tests, F-tests, and chi-squared tests. We will return to these tests later. For now, let's look a little more at descriptive statistics. So here's our data again. This is the 50 experiments drawn at random from a normal distribution with a mean of 5 and a variance of 0.16. When we calculate the average of this specific set of data, it is 5.11, and the variance of the sample is 0.255. I have positioned some of these dots above the others simply so they don't overlap, and just imagine them all on the same line. These 50 experiments were trying to measure the very same sample. Why did they not all give the exact same result 50 times? Because of random errors. None of these results are mistakes, but all of them have some error associated with them. Random errors lead to results being distributed normally. That means they follow a Gaussian distribution. The Gaussian distribution is defined by the mean and the standard deviation. The mean is located at the peak maximum, and the standard deviation controls how widely the distribution spreads out. This curve is a Gaussian curve with a mean of 5.11 and a variance of 0.255. Now I've marked the mean with the red vertical line. The height of the Gaussian curve at any point is proportional to the probability of producing that result in any given experiment. We chose 50 points at random with the probability given the Gaussian curve, and this is the distribution we obtained. The results are clustered more around the mean than in the wings of the distribution. How do we view variance on this graph? The problem is that the units of variance are squared compared to the mean. Look back at the equation. So we take the square root of the variance to produce the standard deviation. The standard deviation can now be mapped on the same graph as the mean because they both have the same units. Square root of 0.255 is 0.505. These blue lines mark the distance 0.505 greater than and 0.505 less than the mean. We say that these lines are plus or minus 1 standard deviation or plus or minus 1 sigma from the mean. If we calculated the area under the Gaussian curve between these 2 points, we get 0.683, which indicates that this region of responses centered on the mean will contain 68.3% of all possible responses given this distribution. If we encompass the area given by plus or minus 2 sigma, which now is represented by the 2 brown lines, we find that this area under the curve gives the result of 0.955, or that we will find 95.5% of all results falling within this area. We can continue out to plus or minus 3 sigma, which can be shown to encompass 99.7% of all possible measurements. As you can see, knowing the standard deviation, which is found from the square root of the variance, is key to being able to describe how confident we are about our results. The mean of the distribution. Generally speaking, people will report their results as the mean plus or minus the standard deviation. Knowing the above results from a Gaussian distribution, you can readily draw your conclusions regarding the certainty or the uncertainty of that result. Sometimes we must make many measurements to determine the variance, and hence the standard deviation for a set of measurements. In other situations, experience informs us as to what the standard deviation will be for certain experiments. For example, we can know that when we make a measurement of weight on the analytical balance, we can anticipate a standard deviation of plus or minus 0.0002 grams. In such situations, we can make a single measurement and assign what we could call the population standard deviation to that result. You will see both situations. We might weigh an object on the analytical balance and report its weight as 6.2489 plus or minus 0.0002 grams. Or we might read the fluid level in a calibrated burette and report it as 12.39 plus or minus 0.02 milliliters. We read the value and report the known standard deviation as the uncertainty in that reading. This is called the absolute uncertainty. It has the same units as the number itself and we can readily envision the range over which we can be certain that a measurement would be obtained. For instance, we are confident that 68% of the measurements we would make of this sample would lie between 6.2487 grams and 6.2491 grams, the value of plus or minus 1 standard deviation, or 1 sigma. We might weigh another smaller sample and find its mass to be 0.2945 plus or minus 0.002 grams. We anticipate the same absolute standard deviation for all measurements on the balance. However, you can perhaps sense that there is another way to look at the significance of these two values. 0.0002 grams is very small in both cases, but it is a larger fraction of the smaller weighing. How does that manifest itself? Well, we can also report relative uncertainty, which is the ratio of the error to the number itself. For instance, the relative error in the first weighing is 0.0032%, or 32 ppm, while the relative error in the second weighing is 680 ppm. We will use both relative and absolute errors throughout our error analysis. Note how the relative error in the burette reading is considerably larger than for weighing on the analytical balance. Different techniques and instruments will have different errors associated with them.